So how do we do it? How do we predict the stress on a metal gear before it's even made? Or figure out what happens with a car crash without actually crashing a car? Well, the answer is this incredible process of translation. We literally have to teach a computer to understand the physical world. And today, we're going to unpack the computational blueprint that makes all of that possible.
Okay, let's dive right in. This whole journey, from a real physical object to a digital simulation a computer can crunch, it's all powered by a kind of universal translator. And that translator is mathematics. It takes all the complex, messy, continuous forces of reality and turns them into a structured, predictable, mathematical model we can actually solve.
But you can't just start building a model out of thin air. Before we do anything, we need 3 core ingredients. These are the absolute non-negotiables, the mathematical components that are the foundation for any solid simulation. Think of them like 3 interlocking puzzle pieces. You absolutely, positively need all 3 to snap together to form a complete picture. If you're missing even one of them, your model is completely unsolvable. It has infinite possible states, which, let's be honest, isn't very helpful for predicting anything at all.
All right, piece number 1, the governing equations. These are the big ones, the fundamental universal laws of physics. We're talking conservation of momentum, conservation of energy. These are the bedrock principles that apply to everything, everywhere. They don't care if you're simulating water, steel, or the air itself. The rules are the rules.
Next up, we have to give our model some character, right? This is the job of the constitutive relations. They basically define the material's unique personality. They tell us exactly how a specific material behaves. I mean, how does steel bend compared to rubber? This is where that difference is captured. And getting this right is, well, absolutely critical. If your model thinks steel acts like rubber, your simulated bridge probably isn't going to last very long.
And for our final piece of the puzzle, we have to lock our model into the real world. We can't have it just floating in some abstract void. We do this with conditions. Boundary conditions define its environment in space, like what's happening at the edges. Is it hot? Is it being held in place? And initial conditions, well, they define its starting point in time. It's how we tell the simulation where and when to begin.
So, we have our 3 ingredients. How does scientists and engineers actually put them all together? Well, they don't just throw them in a pot and hope for the best. They follow a very consistent, very powerful blueprint to build their models.
And this is it. This is that blueprint, a 5-step pipeline that takes us step-by-step from a real-world problem all the way to a solved predictive model. Let's walk through this because every single step is crucial. So first up, step 1, you have to clearly define your system. What are we actually looking at here? Metal rolling, water flowing through a pipe? You got to know the problem. Then, step 2, you identify those big universal governing laws that apply. For most physical systems, that's going to be your conservation of mass, momentum, and energy. Now we start building on that foundation. Step 3 is where you get specific. You develop the constitutive relations for your material. Is it elastic? Is it plastic? Then, in step 4, you apply the specific conditions. The temperature, the boundaries, the forces you're putting on it. And finally, the moment of truth. Step 5, you solve the whole thing. And because of the mind-boggling complexity here, you're pretty much always going to need powerful numerical techniques to get an answer. We're talking about things like the finite element or finite volume methods. This is where the heavy-duty computer power really comes into play.
Okay, so that's the theory. Kind of abstract, right? So let's make it concrete. Let's see how these concepts actually come together in the real world to build these incredibly powerful models.
Not every problem needs a sledgehammer. Depending on what you're trying to figure out, you use a different type of model. For a simple static problem, a basic algebraic model might do the trick. If things are changing over time, we use what are called ordinary differential equations, or ODEs. But what if things are changing across both space and time? Like heat flowing through a block of metal? For that, you need the big guns, partial differential equations, or PDEs. And this is awesome. This is where it all just clicks. If we take a PDE, like this one for heat conduction, and we break it down, we can literally see our 3 essential ingredients right there in the math. You've got these terms here for the material's properties. That's our constitutive relations. You can see you need to plug in initial and boundary conditions, and the whole thing is built around the conservation of energy. That's our governing law. It's all right there, the entire blueprint captured in one equation. But here's the thing, right? Reality is messy. It's really just one thing happening at a time. In really advanced simulations like for 3D printing, you've got multiple models all coupled together. The heat transfer model affects how the fluid flows, which then drives changes in the materials phase, which ultimately causes it to bend and deform. It's this incredible interconnected dance where everything affects everything else.
Okay,
We're on the home stretch, but there is one last absolutely critical translation we have to make. We've got our elegant, perfect mathematical model, but a computer doesn't speak perfect math. It speaks in ones and zeros.
So how do we bridge that gap? We use a brilliant process called discretization. Think of it like this. It takes the complex, infinitely smooth math and chops it up into a grid of separate points, a bit like turning a high-resolution photograph into a grid of pixels. A computer can't solve the whole smooth picture all at once, but it can absolutely calculate the value for each little point one at a time.
And that's it. That is the complete blueprint. It's this amazing process that takes us from a physical object through the universal language of mathematics and into a solvable computer simulation. This fundamental idea is what underpins so much of modern science and technology. From designing safer cars to predicting the weather, it's all about making our world more understandable and a lot more predictable.
So, that leaves us with a pretty big thought, doesn't it? With this incredibly powerful blueprint in hand, a way to translate reality itself into a simulation we can explore, what are the next great challenges we should tackle? What new, complex systems are we going to decide to build next?